It's going to be a pretty short video. We're going to talk about the process called eutrophication. In eutrophication, the short definition would be death of lakes, or simply the filling up of lakes. So what you see here is a picture of algae growing on top of the water. This is a really interesting little algae because if you'll notice, it's got those little green air bubbles, and that essentially helps to keep the algae on the surface of the water, so it acts like buoys or little air tanks that hold it up above the water. Okay, so let's review just real quick. We have our lake here. So a lake has the benthic zone, which is this area along the bottom. It's got silt on it. The limnetic zone, which is where the sunlight penetrates the water, and that's that area right in here. Down below you have the profundal zone, which is where the light gets less and less and less. And then finally the benthic zone is where basically the decomposers or the bottom dwellers or the detritivores live down in this area in this benthic zone. Along the side we have our vegetation growing, and this is in that littoral zone right there where you have your plants growing, your rooted plants, and then your plants that are sitting along the surface. And then you have your riparian zone, and that's this area in here with the trees. Now you'll notice that there are several things coming into this particular picture. First of all, you have you have the thermal pollution that we talked about in the pollution notes, where coming off of this factory or the power plant, you're going to have warm water that's going to come down into here. And when it does, what it does is it helps to remove dissolved oxygen. Okay, and this is pretty important. So it's removing our dissolved CO2, and it's also creating temperature tolerance that the plants are probably outside of what the plants and animals can tolerate. You'll notice that there's also coming in from this side over here another tributary, and it's carrying nutrients with it. So those nutrients we'll talk about here in just a second. So our little lake or pond here has water coming in from non-point source or different parts of the area. Okay, page 3. So here is the process of eutrophication. Just so you're aware, this is a positive feedback loop. Okay, so that means that once the process gets started, it's only going to move in a forward, or it's going to be posited, a forward direction. All right, so what do we have as our components? Well, the first thing is we had that thermal pollution might or might not be there. So thermal pollution might be a piece of this, and that is removing the dissolved oxygen from the water. Okay. Another thing is nitrogen and phosphorus. These are coming from several different sources. One is fertilizers, and another one could be human waste, or other kinds of animal waste, right? And then we also, what we don't show here is some, there are some, well, let's see, how do I say this? We're going to also have oxygen demanding waste. Okay, so this oxygen demanding waste, once again, are things that are going to take out oxygen, right? So they're going to remove oxygen because we're going to have decomposers that are going to use that oxygen in order to consume or to decompose what's coming in from those organics. Most of that oxygen demanding waste are things that are made from organic material. Our final thing here is sediments. So as I told you in our pollution notes, that you're going to have sediments that are going to come in from runoff, All right, so those sediments are going to come in from several different directions, and they may be carrying the phosphorus and the nitrogen with them at the same time. All right, so as they come in here, some things start to happen. One is you'll notice that the sediments start to block off the sunlight, and that's kind of important here in the second step of this. So let's first talk about what happens once we introduce nitrogen and phosphorus into the water. Remember, these are fertilizers. So what are they going to encourage to grow? The thing they're going to encourage to grow is algae. So this algae is going to start to bloom. And when it blooms, it is also going to cut off the sunlight from what's underneath it. Okay? So we have sunlight, and now that sunlight is no longer able to penetrate. So no sunlight is getting past that algae bloom right there. All right, so we have two things then are going to start to block off sunlight. We have our sediments blocking off sunlight, and now we have the algae that's blooming across the top, coating the water with this green or red algae, and it will start to block the sunlight. Okay, so these are growing like crazy, just growing mad. And you'll notice that the phytoplankton is also coming in and feeding off of different things as well. So the phytoplankton is growing. I'm sorry, it's not feeding on it. It's actually growing on the sedge grass. So everything is in high growth when eutrophication starts to happen. However, once you start to block sunlight, remember, algae is a plant, so in order for it to grow, it needs the sunlight. So after a short amount of time, the algae across the top is going to continue to grow, but the algae underneath is going to begin to die. And so when it dies, it's going to fall down here to the bottom. And as it does, then the decomposers, sorry, let me erase that. Okay. Bye, Mr. Easton. Okay. Our decomposers are going to start to go to work and decay or decompose all of this old dead algae down here on the bottom. Those decomposers require oxygen. So that oxygen that's in the water is now being used by the decomposers. So we've now removed oxygen from the water. We no longer have oxygen growing here. And so now things like phytoplankton, things like fish that are swimming around in here, now they were dependent upon the oxygen to grow. Well, now they're going to start to die. And so their little bodies are going to fall down here to the bottom. I'm sorry, that's a terrible fish. So they're going to start to die and fall to the bottom, and then the decomposers are going to take over, which is going to require or demand more oxygen. So now we have our positive feedback loop. Okay, so that's sort of the process that's going on. So what happens is that over time, we're going to have our lake that's going to start to be filled up with sediments and with decaying matter. So that's what's going on here. We have sediments and decaying matter, organic matter. All right, so we have those things down there on the bottom. If you compare and contrast, this is a lake that's undergoing eutrophication. Over here, you'll notice we have a lot of sunlight penetrating here on the left, so the sunlight's coming in. And what you're going to find is you're going to find plants and animals that are able to tolerate or use a lot of oxygen and a lot of sunlight. The water's clear, and the kinds of fish that are present are going to be high demanding oxygen organisms, right? So things that use a lot of oxygen are going to find it here in this left-hand picture. But look over here on the right. We have our water becoming more and more murky, and then we also have our buildup over time. So imagine that this is just building layer upon layer upon layer upon layer upon layer, and it's getting shallower and shallower. So this part's getting more shallow, and it changes the organisms that are in here. So now you have less oxygen. Okay, you're going to have less light, which means that you're going to, over time, have less photosynthesis happen. So you're going to have more decomposers, and you're going to have more organisms that rely upon less oxygen. So it's going to completely change things here. You'll notice that your organisms are going to change. This is a catfish. Catfish swim in murky water. They like it where they don't need a lot of oxygen, so they're going to not use as much. So you're going to have a complete change within that water. All right, so here is another picture of a lake that's undergoing eutrophication. You'll notice lots and lots of algae forming across the top. So this guy's taking a sample of it. What they're going to be looking for is the amount of oxygen that's present and the organisms that are there. So our macroinvertebrates are going to change within this water depending upon what's present. One of the things that I'd hoped is when we went to Lilo that we would be able to take a look at those macroinvertebrates, and you could see how once you start to notice the organisms that are present, they will be an indicator as to the health of that particular water body. This is another picture, so you can see that the water is growing more murky, but there's still some light penetration that happens, but it's real green looking. All right, once again, here is our positive feedback loop. So what that means is that over time, you're going to have your nitrogen and your phosphorus will come in, and they're going to form that layer on top. So our nutrients are going to form a layer, and we'll just go ahead and show it. We're going to have a layer of algae bloom. Okay, but underneath, that algae is going to start to die. And when it dies, it's going to cause the death of some plants over here. And now we have decomposition. And the decomposition are using up oxygen, and then that causes those oxygen levels to fall, which then causes more algae to die, more animals and plants to die, which then is going to cause this positive feedback loop to begin all over again. So there's our positive feedback loop. Okay, so cultural eutrophication. This is a specific term for anthropogenic eutrophication. So what that means is that ordinarily a lake is going to undergo eutrophication naturally. So we have natural eutrophication. And natural eutrophication is going to take centuries. So it's going to fill up, but it's going to take long periods of time for this to happen. However, and this is just in our natural setting, however, when we look at cultural eutrophication, what we're talking about is now we've moved the timeline up to decades. So some of the things that contribute to it are agriculture and industry. Right, so we have temperature variances, we have thermal pollution, and then we have our plant nutrients and sediments coming into the water. All right, notice what this does to the volume of water that's present, right? So over here we have a large volume of water. So even if we were to man-make a lake, we could count on a certain amount of acreage that we could pull off of, right? But notice what happens here. Our sediments have filled up that same space, and now our square footage, our area that we have acreage to deal with, is much, much less. So this is a problem. One of the things that they're talking about is that in North Texas, with the amount of soil exposure that we have and the amount of sediments that are coming into our lakes, they're filling up more and more. So they're left with two different things that they can fixes, I guess. So our fixes are, one, we can build more dams or build more reservoirs. Or two, we can dredge. So what they do with dredging, we can dredge the reservoir. So dredging simply means that they come in here with a big tool. Let's say they come in with a great big scoop, like a spoon, right? And they basically come and start to scoop out and hollow out all the sediments that are in here. And when they do, that actually allows more room then for the water to be able to come back. But that's a problem because there's a couple ways you can do that. One is you would have to drain the reservoir. So take all the water out and then you re-scoop out all of the sediments and then you can fill it back up again. Well, what do you think the problem is with that? I'll just give you a minute to think or a second to think. Yeah, we can't afford to lose our water supply. Now we are anyway over time, right? As this thing fills up, we are losing it, but we can't just drain it all of a sudden. Imagine if you took Grapevine Lake or Louisville Lake and suddenly just said, all right, we're going to drain all of it out and then we're going to dredge it and then we'll fill it back up again. No, I don't think so. So that's problematic. Another thing that they're talking about doing is being able to come in and use machinery to dredge it out while there's water still in here. But now you've got all this water weight that's on top of it and you're trying to clean out what's up underneath. It's very, very difficult to do and extremely expensive, right? So as it gets more expensive, they start to look at the cost, and they say, is it more cost effective to do one, build more reservoirs, or two, dredge it? And right now they lean toward number one. It's just really cheaper to build more reservoirs. But these are huge land grabs, right? So they're going to use a lot of land. And over time, we just don't have it. We don't have the land to build more reservoirs, nor do we have the incoming tributaries to build more reservoirs. It's going to come to the point to where we're going to have to figure out how to do more of this. And that is really, really, that's what makes our water kind of expensive. All right. So here is another picture of eutrophication, and I forget which sea this is, the Black Sea or one of those Balkans or whatever. Baltic? Yeah. Okay. Anyway, so you can see the eutrophication that's happening. You can see that algae bloom that's going on there. Okay, that's eutrophication. So we've kind of hinted around it, talked about it nearly the whole semester, and now finally, hopefully, you can understand exactly